Let us then talk a little bit about charging and discharging. How long will it possibly go on? Charging and discharging for conductors and insulators, and we talked a little bit about charging an insulator last time. We talked about for an insulator. Charging by contact or rubbing or something like that, where you have surface interactions going on. I showed the example of taking the plastic pipe and then rubbing it with some material. And so we said that there's charge exchange going on, right? Or there's some transfer of electrons. Okay, maybe one object is losing electrons, the other is gaining electrons. It's got to obey conservation of charge, though, right? So if you have one object like the piece of clear plastic pipe, another object the silk, and I were to rub it, then there's some contact interaction where the total charge of the silk plus pipe stays the same, but one gains negative, one becomes more positive due to a transfer of electrons. Or what else could be transferred? We said what couldn't be transferred was what? Bare protons ripped out of the nucleus, right? But we could have a situation where instead of electrons, maybe we had ions. Yeah, ions could be transferred. And the mechanism behind it can get kind of complex and is the subject of a lot of research, particularly with the tape. You have materials that are made of hydrocarbons, long polymer chains, right? And if you have some sort of contact interaction where you rip one surface away from the other, then these polymer chains, these hydrocarbon chains, might be broken in such a way that instead of a neutral molecule, you end up with two ions, right? One ion is positively charged, one negatively charged. And, it's the mechanism behind it. We don't know for sure for any particular situation, but the net effect is the same. Okay, and one ends up more positive than the other. Discharging an insulator can be a little bit tricky because, again, if you have an insulator, the charge tends to just stay there. Okay, so if we have an insulator, we can just charge one piece of it. And if you brought an opposite charged particles nearby or an oppositely charged object, you could, if you were able to maintain enough contact, discharge one area, but you can't, for instance, you can't directly get rid of that charge without some sort of contact. There is one method, though, we can use to discharge this piece of tape. So when I was doing the tape experiments earlier in the week, let's see if I can get it charged up. We rip it off, and it's charged up. It's interacting with my hand. So presumably the charge, if there are any extra electrons or extra ions or whatever, they would be on what side of the tape? The sticky side, right? Because that's where the contact interaction is going on. Okay. But then I take my fingers and I rubbed the slick side of the tape. And now it's still got a little bit of charge on it. Let's see if I can get rid of it more. It's so dry in here that's very difficult for charge to spread. let's see if that worked. Yeah, it's pretty good now. Okay. So what did I do? What happened? I didn't touch the sticky side where presumably there are ions or electrons or something, right? Extra charges on that side. So what did I do? Yes. I put ions on the slick side. Okay, so where do those ions come from? My sweat. Yeah, am I a conductor or an insulator? Yeah, I'm actually a conductor, aren't I? Because you have a layer of sweat, layer of water dissolved on your skin, and dissolved in that, or spread over on your skin, and dissolved in that water are ions, salts, right? So you could have sodium chloride dissolved on the sweat of your skin. So let's say, for example, we had this tape, and let me do it this way. So here's a tape, and let's say we have positive charges on the sticky side of the tape. And then here's my hand. Okay, that's a hand. And dissolved on my skin are ions, right? We have maybe sodium chloride, so we have sodium, positive sodium ions, negative chloride ions. So what's going to happen as I rub my fingers over the sticky side, or the slick side? Chloride ions are going to the tape, right? Because we have these positive charges here. They're creating an electric field that's going to attract any mobile charges. And so we end up with a situation where the mobile charges, these dissolved ions, can actually be affected and be moved by the electric field. And so I'm going to leave behind enough chloride ions on the surface, reducing the net charge of the tape, and therefore reducing the overall electric field that it creates until the electric field it's making goes to zero and it's not attracting any more charge. Okay, so I'm discharging by contact in sort of an indirect way. I still have to touch the entire surface because the surface is an insulator, but I'm a conductor, and so there is a source of mobile charges to discharge the tape in this case. What about, let's see, what else do we want to talk about? What about a conductor? Let's say we have a conductor. And we can charge and discharge by contact, right? So let's talk about charging by contact. And let's say I have some conducting object, some piece of metal or something that already has a charge on it, some positive charge. And I bring another piece of metal nearby, which is originally neutral, and I bring them in contact so they actually touch. So what happens to the charge? It actually gets distributed over the entire object, right? Because why? Why in this case is the charge going to distribute over the entire object? Okay, so it goes to equilibrium, right? It's going to reach equilibrium, and these charges are able to spread because what do we have in a conductor? We have electrons that are mobile, right? We have mobile electrons. So in the case of a metal, at least. So imagine two pieces of metal, right? We have a metal sphere and some metal rod. And the electron C is able to spread. In this case, it's positive charge, so it's sort of a lack of electrons, but it's able to spread through one object and through the other as if it were all one great big continuous object, right? As long as there's no gap here, there's a conductive path for the electrons to travel through. So let's see if we can try that out. We have this, which is a Wimshurst machine. And what it does is if I turn the crank it's going to drive two counter-rotating discs with little conductive plates on them. And the brush, there are sort of contact brushes here set up in such a way that it separates the charge. And these two little jars down here are called Leyden Jars, and they're basically just capacitors, ways of storing charge. So we drive positive charge onto one, negative on the other. And then these little probes are in conductive contact with those capacitors. So one gets charged positive, the other gets charged negative. And I should, where did our little scope go? There it is. I should be able to then bring this little device, which is a piece missing. Hopefully that's not going to affect anything. This is called an electroscope. It's just basically just a piece of metal with this little lightweight needle here that's free to pivot. And it's connected to a little probe at the top, and then the rest, the frame of the metal is an insulator. Okay, so it's actually insulated from the central part of this thing. Okay, so if I bring this scope near, hopefully let's crank this up some more. So if I bring this scope and put it in contact with one of the probes, and wait until it settles down. Well, you can even see it now. What happened to the needle? Okay, so the needle charged up, and so now it's deflected, right? So why would the needle deflect if it's charged up? What's happening? Let's draw it. You have this frame here that's kind of in this funny shape. And originally you have the needle, which is, when the thing is neutral, it's just sitting like this. Then you've brought it into conductive contact with a charged conductor. Now the needle's like this. So what happened? It's the same charge everywhere, so what happens to the two pieces that are charged identically? They're going to repel, right? They're going to repel. Let's say it's a positive charge. If I place a positive charge over the entire frame, metal frame here, including on the needle, then when the positively charged needle is near the positively charged center frame, those charges repel until you reach an equilibrium point. And so it's a way of measuring how much charge is on the object, detecting a charge. And then if I touch it, what should happen? It's going to, no, it's so dry. The problem is my skin is so dry, and this thing lost its little probe. Let's see if I can touch it to another object. Let me try touching the bottom. That might help. There we go. There we go. Okay. So I'm a conductor, right? Where did the charge go? Not inside me, because I'm a conductor. It would have to be, spread over the surface of my body, right? So what did I just do? This is sometimes called, well, what I did was discharge it by contact. But when you're talking about discharging by contact, there's a particular special case. If you have an object that, say, it's charged up, and you want to get rid of that charge, and so you have, say, a wire or some conductor that is connected to a very, very large conductor, then that charge will spread out over the entire object, right? And if it's large enough, that charge will be so spread out that it's hardly noticeable anymore, right? What's a great big conductor that we could use to make this charge spread over? Earth, right? What's that called? That's called grounding, yeah. So if you have a wire that's connected straight to the earth. And so here's the entire earth. And sometimes you see a symbol that looks kind of like that to indicate that there's a ground there. So you've got a situation where any excess charge will spread over the entire conducting object. In this case, it's the entire Earth, or may not necessarily be the Earth, might be the frame of a house, okay, which is then in contact with a pipe which goes into the Earth, or the frame of a car if you're talking about grounding a car battery or something like that. Some big conductor to spread out that charge, okay. Let's see. Do we have time to talk about charging? We'll do charging by induction next time, and then we will start a new chapter.